Well, looks like we're back, and here we are again, live for another round of the Tutor Wizard. This is Lecture 3 for the Introduction to Statistics series for spring intersession and for any time you want to watch it in the future. I'm your host. My name is Tim. That's that guy right there. Shall we doodle on his face today? Maybe. I like that eyebrow thing. Let's get some wicked eyebrow things going on here. There we go. Cool. Okay, what are we doing today? Well, let's see here. I just want to check my audio levels. Just give me half a moment. No, we're doing good. Okay, there we are. So yeah, I use Open Broadcast Studio like just about everybody else. So, like I mentioned last time, we were going to continue with a little bit more discussion about sampling, specifically sampling methods. That's what we're going to do first. This isn't going to be an extensive discussion about sampling methods. In many of the courses, these are dealt with through assigned reading. We're just going to talk briefly about some of the main aspects of sampling. When it comes to creating studies and putting together research, there are entire courses that you can take on how to do it specifically for your discipline or faculty that you happen to be in. I know, for instance, the faculty of psychology has a couple of courses oriented towards surveys, sampling, etc., etc. So does the faculty of science. These things are all quite contextual. Yes, I got my window open, and somebody out there is driving their Harley, probably. You can't tell these days anymore. Anyway, far as the descriptive statistics goes, we're going to get into box plots, or I like to call them box and whisker plots because I'm old. Bar plots, we'll do some histograms, stem and leaf plots, and talk about some scatter plots as well. And again, these I'm just hitting the main topics because there's other plots too. There's the ubiquitous pie chart, which is, well, for many, many years, it was one of the favorite charts to illustrate percentages. And I remember the magazine, newspaper, USA Today just milked that cow to death. Not my favorite plot either, but we'll talk about a few other ones maybe as the course goes on. There's some interesting new ones on that you see in research and in data-oriented publications these days. So something maybe we'll look at in the future. Well, let's see what else can we mention here. I know you were probably thinking, shouldn't this be Adrian tonight with more history of math? Well, Adrian's actually taking a bit of a holiday. And he needs one because, time waits for no man. And I hear tell that there might be a wedding reception that he's attending, which might lead to some interesting stories when he returns. We'll find out about various levels of inebriation and flirtation. We'll see. And we'll see if anybody wants to bite on that one. He might actually be listening to this stream tonight. We'll find out all the glorious details when he's back. Anyway, we should probably get started with this because there's going to be a lot to talk about tonight. This could be a fairly busy one this evening. Let's have a look. Let's go to our next slide. Okay, now where'd my slide go? All right, let's back up. Where's my slides? Where's my slide? I don't see a slide here. Where's my slide? Ah ha ha. Okay, some reason I have a blank slide there. That's kind of weird, actually. I must have accidentally tapped something. Let's just, I'm using Open Board, by the way, for software, if you're wondering what I'm using. Yeah, there's that one right there. Okay, I must have clicked something inadvertently. No matter. Open Board's pretty cool piece of software, too, by the way. You may want to check that out. It's free software, and I believe it runs on Windows, too, but I'm running on a Linux platform here. I use OpenSUSE's or OpenSUSE, depending on what part of the world you're in. I use the rolling release called Tumbleweed. Yes, it makes me a snob, I know. Anyway, so here we are with a simple random sample tonight. I'm feeling a little wobbly as far as narration goes this evening, so I might wander off a little bit and talk about strange things. I hope you're okay with that. Well, I do it anyway, but whatever. Anyway, simple random sample. This is the easiest way to collect a sample. You are going to randomly select your participants or the subjects of your research. The hard part of it isn't the simple part. We can always make things more complicated. The hard part is the randomness. Where are you going to get random numbers? Or how do you choose things in a random manner? Well, there's a number of ways. In the back of many textbooks for statistics, you could often find a table of randomly generated numbers, and historically those numbers truly are about as close to random as you can get. And you can find the tables online as well, and includes the methodology used to generate them, which isn't at all straightforward. I see you have an ad break going right now, so we'll just wait for that to run out. What's our first ad tonight, by the way, here? No, it looks like gaming. Yeah, it is. That's fine. I bet that's looks like a new Doom. What are you? I'm trying to guess here at this. Looks like the BFG 9000 to me. Could be wrong. Could be wrong. Yeah, it is Doom. Yes, that was scandalous back in the 90s. The BFG 9000. Ooh, edgy. Yes, the big freaking gun. But a bigger gun would have been the BFG 9999. Just saying. And there's my favorite skip the dishes ad. Yeah, just skipped you, loser. I'm easily amused. You probably have figured that out by now. And now we have a movie ad. That's okay. Yeah, I think I'll be taking a pass on. Well, no, actually, maybe. Might go see it. Nah, who am I kidding? I'm too old for that. And we're back. Okay. How do you get random numbers? Well, you can get tables of them, and a legitimate table of random numbers will come along with an explanation of the methodology used to generate that. If you're thinking about using a random number generator from software, Microsoft Excel comes to mind, or any other spreadsheet software random generator, generally speaking, they are technically pseudo-random generators. The numbers they generate will eventually repeat. So, yeah, if it's something that absolutely must be random, that's not it. Random password generators on a computer are a bit better, especially for public key cryptography. Oftentimes what they do is they'll sample the electronic noise in the system that you're generating the keys on. Plus you'll bang away like a monkey on a drum on the keyboard to also generate some randomness. Once they have enough, they'll generate a fairly secure random key, and can be used in some cases to generate random numbers as well. Anyway, my point is randomness is hard to come by, so pay attention to it. But for most simple research, you don't have to get stupid crazy with random number generators. I just like to always warn people that just because it says, hi, random numbers can be generated by calling this function, doesn't mean it will work that well. Anyhow, simple random sample is, well, I guess I should make a note of this, huh? Because if you're going to make notes, better than I should write it down instead of just having to listen to me blather on. So I'm using red ink for some reason tonight. Okay, use a table, we'll fix that in a minute, of random numbers. And these can be found if you go looking for them. Boop. Let's go back to blue here. Okay. Check how the numbers were generated. I suppose you could even visit your local game shop and pick up some 10-sided dies. That would work, provided, that they're not biased in any way. That's the hard part with dice, by the way, is how do you get a perfectly balanced die? Casinos go out of their way to make that happen properly for games like craps. Okay, so use a table of random numbers. If you must, you could use a RNG, boop, 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 random number generator. Okay, my handwriting tonight is terrible, but that's because of the system I'm using. Generator. There we go. Boop. If you can't get random selection, what you can do is random assignment. That's always a way around that. I'm just trying to redo that word. Random number. There we go. Easier to read. So random assignment. So if you're not particularly happy with how you managed your selection of subjects for your study, and you have more than one category in which to put them, you can, after doing your best with a simple random sample, do random assignment to different groups. That would make sense. There's ways around this, ways to handle these problems, which kind of go way beyond anything you need to know to pass this course. So we're not going to spend a lot of time on it. But a simple random sample means there's no methodology behind the selection of participants, and we're using some form of randomness to choose the participants. And that's a great place to start your understanding of sampling, an SRS, which is oftentimes how we refer to this, the simple random sample. Let's move on. There's other things to talk about. For instance, if we're not doing it randomly, that means we must have a system, hence the systematic sampling method. Okay. Well, I'm pretty sure everybody knows what system means. The idea is, if you have a list of potential subjects, you may want to say that if it's an unordered list, so it's not alphabetical, because nothing about first names starting with letters is random, but let's say you have an unordered list. You may say that I'm going to choose every fifth name on the list. One way to do it. Or a systematic sample, if it's some other characteristic and you want it to be representative of the population. So here's where, let's say we're interested in people or things that fall into certain categories, and each category has a certain percentage of in the population. You may want to specify that, okay, I want 25% of my participants to be from category A, or, to be a member of the population with characteristic in category A, and maybe another 15% from category B, and 30% from category C, and the remaining percentage would be from category D. That way, as far as the characteristics go, you have a representative sample. So a systematic sample then means that you're going to implement some method. Implementation of some selection method. And like I said, there's many ways to do this. It really comes down to what is it you're trying to identify? What is it you're trying to study? And again, how difficult is it to do it? I mean, you can make a systematic sample so difficult that it would take you a month of Sundays. It's a silly saying, but I'm old. But you can make this too hard. So you want to keep it simple. So even though you have a system, keep the system easy to understand, because if something goes wrong with your sampling and it's not working the way you thought it should, if you have a complicated system, it's going to be a lot harder to figure out where it went wrong. So keep the system simple, or at least keep it understandable. That's a good word. We'll use that. Understandable as well. The other thing, too, is you could design a system and then you have somebody implement the system, but if they don't truly understand what it is you're trying to do, you're going to end up with problematic data. So, again, give it some thought. You don't have to fear creating a system. You just have to be reasonable when you put together a sampling method. Sometimes I remember I was going to suggest out of the phone book, but again, names in a phone book or business names or people names in a phone book, they're alphabetical. And there's going to be a lot more of them starting with the letter H than the letter Q. So you just can't say, well, take every 10th name because that's not going to work. Systematic samples, I suppose, would be the random number dialers that telemarketers use these days to call people on the phone. You can specify the three-digit exchange number. You could specify a range of numbers for the four-digit what do they call them? Yeah, suffix numbers, I guess is what they are. You can specify area codes. So using auto dialers can make systematic outcalls a lot easier. But again, that's countered by the fact that nearly everybody, they don't recognize the number, they're not going to answer the phone. So, you probably have to be a bit clever about it. Again, one of the things you can do if that's what you're trying to do using auto dialers, you could, I suppose, once you do manage to collect a group of participants, then you can randomly assign them to different subcategories. You want that randomness, and sometimes you have to go to extra steps to get it. Anyway, let's move on. Next slide. There we go. What's an observational sample? Well, now what we're really getting at here now for this slide, the next one for sure, is how much hands-on do we want to get? Because for many things, if you are actively involved in the measuring process, it's highly likely that you're also affecting the process that you're trying to understand or study. If you're trying to study the behavior of animals and they see you watching them, I'm pretty sure they're going to change their behavior. So the use of a blind so that they don't know you're watching them. Yes, it's voyeurism. That's what we're talking about. That's one thing you can do. If the animal happens to be human and they're shopping in a grocery store, you can pretend to be a shopper. You just sort of walk around and observe things. Most people probably wouldn't think twice about that. Or you can watch the CCTV cameras. Then you're definitely out of the picture, so to speak. In a lot of older grocery stores, for instance, there's a walkway on the second floor with windows looking down on the aisles. Well, that's a perfect place to watch the behavior of shoppers. There's lots of ways to do it. One of the more high-tech ways I've heard of, I've never actually seen it done, but if you use the RFID tags in products, and the shelves are also wired to read RFID signals, the fact that someone picks up a product and looks at it, that lodges a data point. Now, if they put it back on the shelf, that means that's a data point where the shopper has picked an item up, for whatever reason, looked at it, but then chose not to purchase it, so it goes back on the shelf. That's valuable information. If they pick the item up off the shelf and it doesn't go back on the shelf, then it probably went into the shopping cart. If it didn't go into the shopping cart, we call that shrink. How would we detect it? Well, if the RFID tag doesn't get scanned at checkout and it's not on the shelf, then it went out in somebody's pants. No, that's not a weasel in your pants, sir. That's my Ovaltine. I just thought of Ovaltine. I have no idea what the connection between Ovaltine and weasels in somebody's pants are, but if you think about it, it's probably a good premise for a movie. considering the carpo that Hollywood's been putting out lately. Okay, what, nobody's going to jump on that? Weasels, Ovaltine, pants? Observational sample. Okay, so the beautiful thing about the observation, let's make a couple of notes here. So an observational sample then does not interact with the subject. Now, remember, oftentimes if the subject knows they're being observed, it's going to change their behavior. So you don't want that. This is a fairly low-cost way of doing it because you don't need to get overly involved. You basically just have to quietly watch. And you can't find much cheaper way of doing things other than watching. What else can we say about this? I don't know. I was rabbiting on there quite some time. The most important thing is that it does not interact with the subject and therefore does not affect the subject's behavior or its characteristics, depending on what it is you're doing. So that's a good thing that you may want to do. We'll probably come back to some other topic here in a minute. I just thought of one I did leave out. Now, we're not going to do the experiment yet. That's where you do interact. I'm going to put another slide in here because I missed a topic I should have talked about, and we'll do it right now. It's called the self-selected. Not the same, really. Okay, what happened there? Let's hit the old Control-Z button. There we go. Self-selected. These are terrible. Don't trust these. Bad, bad, bad. No, 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 bad. Yoink. There we go. So a self-selected sample is where the participants choose to participate. Radio stations do this all the time. TV stations do this all the time. Now the internet does it too. If you get to choose whether or not you wish to participate or not, you're participating in a self-selected sample. So the subjects choose themselves. There's a problem with this, though. Subjects choose themselves. It leads to bias. Why? Well, the effort it usually takes, the motivation is a better word, I guess, to get involved with a sampling process, a questionnaire or something, usually requires people who feel very strongly about the topic. Either you're really against whatever the question's referencing, or you're really in favor of whatever's being questioned. The people who are neutral, however, usually can't be bothered to vote. And of course, then there's also the business of repeated votes, and you see this on social media all the time. So these are bad ways. If someone asks you to review a document analyzing data from a self-selected sample, yeah, about the most you can say about a self-selected sample is it represents only the people who participated. If you are thinking to generalize this to something beyond the group of people who participated, it's not going to work because it's heavily biased. So this is not generalizable. Now, what do we mean by generalizable? Generalizable, is that an ABL or an IBL? Well, it's an ABL tonight. Remember from an earlier discussion, if we want to understand a very large population, we need a representative sample. And if we collect that and analyze it carefully, generally speaking, we get very good, very accurate generalizations to the larger population. But the problem with self-selected samples is they are not going to be representative of a population, and therefore they're not generalizable. So yeah, it's makes for interesting, I suppose, discussions on social media. And when I say interesting, I mean flame wars. but they're not worth much. So yeah, self-selected samples that turn up in research, research isn't worth much. You would be wise to, yeah, say you reviewed it and put it aside as, okay, an example of how not to do things. Okay, so not generalizable. How can you do generalizations? Well, it comes back to the representation of the population in your sample. If you can get well chosen data that accurately reflects the population, then it makes sense to think about generalizing that to the larger population. There might be other criteria you want to look at. If you're studying people who generally exhibit certain characteristics, well, they're not. You can't generalize that to the entire population of the country because the country's full of people that don't meet those criteria. But when we talk about generalizing to the larger population, what we do mean is that the population of interest. So I'm trying to think of some character. Let's say people who are diagnosed with autism. Okay, so you're on the spectrum. Okay, your population is the people who have a medical diagnosis, not one off the internet, who have a medically diagnosed score on the autism spectrum. And if you're going to study those folks, then you want to have your sample represent them. And you can generalize to them, but you can't generalize beyond them. That's where you have to think carefully. Okay, let's move on here to experiments. Now, here is where you can, if you're careful, this one you do interact. You do interact in some manner. You do interact with your subjects. Now, of course, there's lots of ways to do experiments. You can do the old Skinner box method, like train the rats to run the maze. You're interacting. Or you can, in medical research, check the efficacy of some new drug. But of course, an experiment often needs a control. So how do you know the new drug actually worked? Well, you can measure the new drug's efficacy against the old drug, but you should probably also have a control group who's getting a placebo. So it's only through experimentation and careful control of all the extraneous variables as much as you can. It's not easy to do, but you want to control them as much as you can. So experiments will use controls. So this is, the old placebo. So you're getting the sugar pill. You can use blinding. I never did finish my earlier thought. I got thinking about this. We'll finish that here in a minute. So what do I mean by blinding? Well, that means if you're testing a new medicine, well, nobody involved with the administration of that, including the patient, knows what they're getting. Everything is just a little white capsule. Nobody knows what's inside it. And if you do full blinding, even the experimenters don't know. The only information that's recorded would be some ID number on a particular dose. It's only when the experiment ends that the ID numbers are cross-referenced to the list of numbers that had either the active ingredient, the old ingredient. I'm talking about medicine here, so the active ingredient would be the new drug. The gold standard is how they often refer to the old drug. You'd have the control. The only time anybody actually knows which ID number belongs to which of those categories is when the experiment is over. And then you can analyze the data. Okay, so the use of controls and blinding helps include, or that's not the right word, helps to ensure validity and reliability and usefulness of your study. So when we're interacting with subjects, There's usually, if we get away from the medical aspect, I suppose, a little bit, you can also have, and we're coming up to scatter plots, well, this is going to dovetail to that, but if there's a variable that you want to manipulate, well, we usually call that the explanatory variable. And the thing that you're measuring is the response variable. So if you're going to manipulate dosage, for instance, how does increase the dose? Does blood pressure fall? Increase the dose, does the heart rate go up? Does it go down? Those are response variables. And the idea is that if you design everything carefully and try to control as many extraneous variables as possible, you just might be able to say that there's a very strong relationship between the thing that you've been manipulating and the outcome of the experiment. I don't want to say causes. I'm not saying A causes B. I'm just saying that you can establish a strong correlation, and then further research from there may cement the relationship a little bit more firmly. Anyway, so experiments will often use controls and blinding. You are interacting with the subjects. Of course, you have to be careful of that because interaction, everything you do is going to make a change. And this can be generalized quite nicely. Again, representative study, though, right? Possible to generalize. Etc., etc. Okay, let's move on to the next one. Now, retrospective versus prospective. Well, what does that mean? Well, retro means looking in the past, and prospective or prospects means looking in the future. And this describes how you get your data. Much research is done retrospectively. Again, medicine's probably an easy way to do it, or I guess you could analyze tax returns too. You could analyze a lot of things that are historical. So let's stay with the medical theme, historical. Let's see here. So let's say you want to look at the medical outcome of a population of people who had diabetes. And with their permission, you're going to access historical medical records. And from there, you're going to pull out the data, the characteristics that you want to study, and proceed from that point of view. So looking backwards at historical data is a retrospective study, and if you're of a population, so it would be a retrospective sampling. Future means that, well, there's no records to involve. What you do, though, is you track patients or track participants going forward. Maybe every month or every 6 months or even once a year, you bring in your participants for an interview or some measurements. Medicine does this quite often. Then you, over time, gather the data, and usually you set some end period. 5 years, 10 years, 30 years down the road, whatever makes sense in context of the subject. Once you gathered that data, then you can analyze it. So this is all about future. So this requires tracking of participants. Okay, I'm not writing that word very well. Let's just get rid of some of that nonsense. Let's try again. Participants. I'm participating in your pants. Whatever. Anyway, tracking of participants. This is oftentimes a long timeline, especially when you're tracking the lifespan, the life characteristics of people. Lots of animals, a lot of creatures aren't long-lived, so zebrafish and fruit flies are oftentimes, creatures of study because they have short lifespans, so it's easy to collect prospective data from the moment they hatch until the moment they pass on to the great fly graveyard in the sky. So it depends on what's going on. Long timeline for people. That seems to be a better way to finish that off. There we go. Okay, there we are. That actually looks like for people was a pineapple. You know what? It's the word people. Good enough. So, prospective studies looking forward has a long timeline, requires tracking of participants, and yeah, it's actually, it's not a bad way to get I'm trying to find the right word for this. Um, Temporally relevant data. You're saying, well, that's a loaded phrase. What do you mean by that? Well, when I was younger, there was still tetraethyl lead in gasoline. And when the internal combustion engine for up until the mid late 70s, gasoline generally had that lead compound, which was used to make your engines last longer. It was a cost saving measure for manufacturers. The politics of that's not the point. Oh, we got an ad. I'll wait for this and then we'll get back to tetraethyl lead, which is an interesting one. So we have someone running around a campfire here. Oh, we're... Okay, I don't know what this ad's for. What are we doing? Oh, drinking wine. Oh, happy people. There we go. One down, two to go. Do, 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 do. Oh, this is the skip the dishes ad. Yeah, I'm doing play-by-play color commentary for a skip the dishes ad. Is that bad? Oh, sorry, DoorDash, my bad. Oh, and then we have this one. Okay. Oh, honey, don't hold the microphone. You'll make it vibrate. You don't want that. See, true pros never hold the microphone. No, 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 no. Take your hand off the microphone. That's good. No. All right, whatever. Fine, be like that. Yeah, see? It bounced. When she took her hand off the microphone, it vibrated. Silly, silly, silly. Tetraethyl lead has severe central nervous system effects. And if you think about the urban environment, heck, you think about the rural environment that many, many people grew up in. They, and myself included, would have all been exposed to that, varying degrees of lead poisoning. It's not just the old joke about lead in the paint. There's lead in a lot of things, none of which is good for your central nervous system or your mental health for that matter. So if you want to see something really interesting, and this would be a retrospective study example, then look at the rates of violent crime and how they correlate with the decreasing quantity of lead in fuel. I know there's a number of American studies that have very interesting outcomes from that. Now, that's the problem with a retrospective study. Looking backwards, you have to take into account that things were different in the past. A prospective study allows you to tailor your research according to the current economic or the current environmental climate. And if you need to make changes, then you can think about it ahead of time and maybe make a few changes. Although generally, once you start a study, making changes is probably not the thing to do. But you don't know, the future being unpredictable, you may have to do that. So there's some advantages to a prospective study in that you don't have to modify your results to take into account characteristics that are no longer present. Okay, let's move on. I think that's about it for studies. Yes, now we're into, let's talk about how to describe data. And this is one of my favorite methods. It's the box plot or the box and whisker plot. There are 10 numbers in this data set. I believe there are 2, 4, 6. Yeah, I got 10 numbers up there. The average is 33.3. And there are, the rest of the information we're going to pull out of here as we make our way through construction of a box and whisker plot. What we want to do, is come up with the 5 numbers summary, because that essentially gives us what we need. So the 5 numbers summary is the minimum value, in other words, the smallest, so that's 8. And then we have the first quartile, Q1. We'll get to that in a minute. The second quartile is also called the median. We'll grab that as well in just a moment. Then we have Q3, the third quartile, and then we have the maximum value. The largest value here is 60. So the range then is 60 minus 8 for 52. All right, last lecture we talked about the median, and the median is halfway. So with 10 objects, or 10 observations here, we're going to have to take the average of observation number 5 and observation number 6 to get the halfway point. This would be y1, this is y2, this is y3, y4, and y5. That makes this y6. I'll just finish this off. y7, y8. You're going to be y9, and this one is y10. It's supposed to be a y, whatever. Anyway, the median then is the average of those two numbers. So 29 and 30 gives us 29.5. Now this cuts our data into a lower half and an upper half. And the middle value here, 25, this is Q1. Okay, got that. And 35 is Q3. So the 5 numbers summary will allow us to draw a box and whisker plot. So let's try to do that. Let's get this tool here. So we're going to draw it vertically because I'm going to doodle some more on here as well. I don't know exactly what we're going to... Yeah, we'll do it this way. This is not to scale, by the way, because... well, it's just not. It's just a representative box plot, but we will label it appropriately. There we go. Now, Q1, so the box is this, whoops, that's not what I wanted to do. One moment, please. I keep forgetting to switch my pen back. So the box is this region here. If we're starting from 0 and going to infinity, then Q1 is the lower part of the box, and Q3 is the upper bound of the box. So Q1 was the number 25, Q3 was the number 35. I have not labeled max and min yet because we're going to calculate whether or not we have outliers. So that's why I've left that open. Now, what is the median? The median is 29.5, which is pretty much right in the middle. So let's make a line here, and we'll call this the median, or Q2. It doesn't matter. Either one works. 29.5. All right. Now, there's some things we need to find out about. We need to know what the interquartile range happens to be. Well, the interquartile range is Q3 minus Q1, so that's just 10. That's how many units the box spans. I'll write this out in case you're trying to keep the sound down. Interquartile range. Okay. We need that, by the way, to calculate whether or not we have lower outliers or upper outliers. Let's move this around a little bit. All right, so here's a formula. We have to compute what's called the upper fence, and we need to compute what's called the lower fence. This is how we're going to define an outlier. The upper fence will be a value that any number or any observation larger than that value is an upper outlier, and the same for the lower. So upper fence will be Q3 plus 1.5 times the interquartile range. So Q3 was 35. The interquartile range was 10. So this is going to be 35 plus 15. So the interquartile range with this formula then says our upper fence is at 50. So what we'll do for the upper fence is we'll make a horizontal bar right there. Now, what's our largest number? 60. But is there any other numbers bigger than 60? Well, let's have a look. I believe there's a 58. So that means 58 and 60 are both upper outliers, and we typically represent them with dots. So now we can say that 60 is the max, and this observation is also 58. The fence is at 50. So let's just call this the maximum value right there. The fence, we'll just label that for clarity, that's at 50. Now we're going to do the same thing to find the lower fence and also whether there are any lower outliers. What's our two smallest values? We've got 8 and 25. I'm pretty sure 8 is going to be a lower outlier. Let's find out. So here we have the lower fence. Now this will be Q1 minus 1.5 times the interquartile range. So Q1, I said, was 25, and we know the IQR is 10, and 1.5 times that is 15, so this gives us a lower fence at 10. So we'll make a horizontal bar there. Well, you know the number 8 is the minimum. Boom. And the lower fence is at 10. And now we have a box and whisker plot. One of my favorite ones. Now the box and whisker plot will tell you a number of things, but what it doesn't tell you is what the actual observations are. It tells you the distribution, the pattern, as we discussed yesterday or in the previous lecture. There's a pattern to the data, and the box and whisker plot will illustrate that pattern, but it's not going to identify the entire data set. Sure, we see this 60 and the 58 and the 10 down, or pardon me, the 8 down below. Those are specific values, but the rest of the values could be averages or computed. So the advantage to the box plot is it gives you a pattern. The disadvantage is it doesn't give you specific data. So let's make a note about that. The advantage is it illustrates a pattern in the data. So if you're asked, the data skewed? Do we have a longer left tail or a longer right tail? Well, you can judge that by looking at how long the whiskers are. Is it reasonably symmetric? Well, is the median in the center or close to the center of the box? These things can all be approximated. That's a good way to put it. What is a disadvantage? Well, it only generalizes the data. It doesn't give you specifics. There are few, if any, specific points. Maybe specific isn't the right word. When I say specific, what I really mean is actual observations. Usually, like with the second quartile, the median, and that was the average of observation 5 and observation 6. It's not an actual observation in the data, it's a calculated observation. Anyway, that's our box and whisker plot. We had a few more of these to make our way through, so let's get cracking. Over here we have a histogram. So the histogram and the bar chart are very similar to each other. The difference is, you'll notice the histogram, for the most part, the bars are all touching. I've left a gap here simply to illustrate how to handle it if there is a gap in the data. You'll notice over here on the bar plot, the bars are all separate. They're not touching. We'll get to that. Now, the most important thing to know about this is when you're looking at a histogram, you have to know, are you including the right endpoint? And if you are, then you have to be excluding the left endpoint for each of these intervals. So each one of these bars is an interval. And if you've ever done calculus, you know that we have half open intervals. So this is an open bracket, and this is a closed bracket. It can be the other way around. We can start with closed, but if we do, we have to end with open. So what do I mean by that? Well, typically, we're going to use, I'm going to use the left endpoint or the right endpoint on this one. I think we're going to use the right endpoint. This will be the right endpoint, and I will try my best to explain this to you. If you've done calculus, you'll know, oh, this is easy. But if you haven't, you deserve a reasonably good explanation. So if we were looking at numbers, let's say between 0 to 1, and we had left endpoint is open, right endpoint is closed, we will never have exactly 0 at the lower bound. We can have 0.0001 or as small as we like, but never exactly 0 for the left endpoint. On the right endpoint, however, we can be exactly 1. That means the new interval then is going to start at 1.0001, or however accurate, how many decimals you're chasing around, and it'll go up to exactly 2. So you'll see this is why we can't have both closed or both open are on the horizontal axis. So right endpoints mean you're including the right endpoint number, but you're excluding the exact left endpoint number. Conversely, if we had it the other way around, we would start at exactly 0 and go up to 0.9999, or however many nines you want to chase around. That's fine. And then we would start with a closed interval again. This will be exactly 1, and this will go up to 1.9999 again, and so on and so forth. So you need to know what endpoint is being used to interpret one of these histograms. So we're going to say that we're using right endpoints. Okay, so this is going to be from 0 to 1. This will be from 1 to 2. This will be from 2 to 3. This will be to 4. This will be to 5. This will be to 6. And this will be to 7. Okay. Now, you'll notice there's 2 vertical axes. I've labeled this one as frequency, which is just another way of saying counts. What's on the other side? Make some room over here. This is called the relative frequency. We're going to use percentages. I'll show you how to do that. Relative frequency. Just abbreviate that for now. Let's move back a little bit. Now, the height of the bar tells you how many observations are in that interval. Let's write that down. Height equals count. So for instance, this one, the first one, from 0 to 1, there are 2 observations in there because the height goes up to 2. I don't know what they are. Histograms will never tell you what the data points are. They only tell you the frequency. That's all you're getting out of here. Now if we look at the second one, so remember now this is from open interval 0, closed interval 1. Now we got open interval from 1 to closed interval 2. But how high is this one? This goes up to 5. This one goes to 4. This one goes to 8. This is just 1. There's 0 here, and there's 1 here. So by adding all the heights, we can find n. How many observations are there? So I got 1 here, and 1 there is 2, and 8 is 10, 14, 19, 21. Oh, that's a terrible number to divide. Okay, I've got my calculator. We'll use that. Okay, I was hoping for 20, but don't get what you want sometimes. That's fine. Am I making a mistake to save my bacon? No, I did not. Okay, so we have n is 21. Now, how do I turn this into the relative frequency? Well, the relative frequency then is simply the count. So let's look at the first interval. That's going to be 2. Oops, hang on. Let's do it right. That's going to be 2 out of 21. So that's going to be just a little bit under 10%. Usually relative frequency is done with decimals, so we'll just do that really quick. 2 divided by 21 is 0.095. So here we have 0.095. And if we look at, oh, wait a minute, I put that in the wrong spot. Okay, I gotta tinker with this. One moment, please. Where's my eraser? Let's get this out of here for now. Don't have room for you. I put the 2 out of 21 in the wrong spot. Just give me a moment to fix that up. Where's my grabbing stick here? Yeah, there it is. That has to be up here. There we go. Now let's come back over here. This one is 1 out of 21. That's for these two. The 2 out of 21 was for the first, so that's fine. So 1 out of 21 is going to be 0.0475. There we go. And we can do this all the way up. There is no 3 count. There's a 4 and a 5 count. So the 4 count here, 4 out of 21, that's going to be 0.19 unless I've screwed up. And then we have 5 out of 21. So that's going to be 2375, I believe. And then we have 8 out of 21, which is 0.38. Now, if we've done everything correctly, that better add up to 100%, or I've made a mistake. So let's find out. So I've got 0.095, with some rounding, of course. This is not going to be perfect. Plus, there was 1 at 2. Then I've got 2 at 0475. So that's another one of those. Then I've got a 0.19, and then I have a 0.2375, and then a 0.38, and that adds up to 99.75, so good enough for me. That adds up to 100%. So in other words, it's a probability distribution. That's another way to think about it. Now, what can you do with this? Well, you can answer some questions off this. I could ask you, well, let's get back onto that first so we don't mess up. We could say, what percent is greater than or equal to 4? Okay, so this is where the endpoints come in. Greater than or equal to 4. Remember, this one has an open start at 3 and ends at exactly 4, which means I have to include the 8, and then this one for 9, and this one for 10. So that would be 10 out of 21. And what is 10 out of 21? Let's find out. 10 divided by 21 is 47.6. So 47.6% of our observations are greater than or equal to 4. But let's say it was just greater than 4. That doesn't include the equal sign anymore, now does it? Am I using the right endpoint? Oh, hey, I totally, yeah, okay, so sorry about that. This is wrong. I've sketched this out as left endpoint included even though I was talking about right endpoint earlier. My bad. That's what happens sometimes when you're thinking about stuff and doodling at the same time, so let's just make a note about that. We are using left endpoints here. Okay, whatever. Okay, so we're using left endpoints. No, I had that right. Okay. Boop, 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 boop. Control Z's your friend, by the way, on the keyboard. We are using right endpoints. It's the included point. Okay, there we go. Okay, so using right endpoints. Now, if I'm greater than 4, that means I'm not using the fourth column here. So by changing from greater than or equal to 4 to simply greater than 4, now it's only 2 out of 21, which is, oh, well, let's not mix our units up. So now we're at 9.5%. There we go. So this is the kind of question you can get asked on a midterm exam. Actually, a final is kind of a fair ball exam on that one, too. Anyway, the only time there should be a gap on the horizontal axis for a histogram should be if there's no observations in a particular interval. So that's how you use these. One of the ways you can use the histogram. I should make a comment about what the axis requirements or the axial requirements are. So the thing you have to keep in mind for the histogram is the horizontal axis. Let's try to pick that right. So the horizontal axis is going to be numerical. Numbers. The vertical axis will also be numerical. You're saying, well, that makes sense. Well, it does until we get to the box plot, or pardon me, the bar plot, which is coming up next. So numerical, numerical. Let's look at the bar plot. Now, this is categorical. The horizontal axis is going to be categorical or nominal data. Categorical. And it must be at least an hour into this trip. Now that's why I'm getting all talked out. Holy moly, yeah, it is an hour. You can have numerical on this axis, though. So the conversation about whether you have a relative frequency over here or a numerical or just frequencies on this one, it's the same thing. It's just that the explanatory, or let's not call it the explanatory axis, the horizontal axis has to be categorical for the bar plot. Otherwise, you pretty much read it off the same way. How high is this one? This one's 4. This one's 3. This one's 7. And this one is 5. So how many observations do we have here? We have 19, apparently. Wow, I can really pick some lousy numbers to use. So just by counting the heights, we see that n is 19. So height gives us our frequencies. And if you add them up, you get the counts. Again, the same idea. If I wanted to know what percentage are blue, we could say what percent are in the blue category. Well, blue has 3. 3 out of 19. All right, let's see what that is. 3 divided by 19 is 1579. We'll just call it 158. Boom. All right. If I wanted to know what percentage are blue or red, well, blue or red means I'm going to add 3 and 4. That's 7 out of 19. So what is 7 out of 19? That's got to be, oh, I don't know, 31 and a half. Another 6 maybe, I don't know, let's call it 36 and a half. I don't know, let's find out. 7 divided by 19 is 36.8. There we go. So this would be 36.8%. This would be 15.8%. for that one. So you can see the questions can be asked and answers can be found in a very similar manner. The only thing that's different is that that's categorical data. That's all we're going to say about that, because anything else, basically, I'm just repeating myself. Moving on to the stem and leaf plot. Now, the stem and leaf plot is kind of like a histogram, but it also tells you the values in your data set. So you can actually read them off. I could give you a stem and leaf plot, and you could construct a bar plot, or not a bar plot, a box and whisker plot from the data. So the first thing you have to do is choose the stem. This is like a plant. You've got a stem, and then you got leaves coming off, and that's the analogy that we're going to be using. So the first thing we have to do is choose the stem. Well, we note the range. Look at the range of the data. So you'll notice the data range from 1 to 45. So it seems to me that, so we start from 0, 1. I'm doing that in a specific reason. I'll tell you why in a moment. 2, 4, 5. So that suggests that it would make sense to have the stem be 0, and then the 10s, the 20s, the 30s, the 40s. So the stem will be the tens column. And that means the unit digits, the single digits, will be the leaves. Okay, so here, I didn't leave myself a lot of room there. Let's fix that up. Yibbidoo, move that out of the way. There we go. Back over here. So we're using tens for this one. Oh, we got an ad running. Okay, I'm not going to jump here. Okay. I'll do a little preparatory work while we're running the ad out. And I see we're back. Okay, cool. So you haven't missed anything. I'm just doing a little sketching. So we're choosing the leaves to be the ones, the rightmost digit, and the stem will be the tens. So here we have, well, didn't change my marker back. Should know better by now. So here are the tens. These are the ones. Now you can start from the smallest and go down, or you can start from the largest and go down. It doesn't really matter. I'm going to start from the smallest, zeros. So this would be, here, let's try this, a little bit more room. So this will be 0, 10, 20, 30, 40, 50. Now I'm going to use the 50 just to illustrate something. Now let's look at our numbers up here. So the number 1, that's just another way of saying 0, 1. Okay, so we're going to put a 1 here. So 0, 1, that's our first observation. I have 2 2's now. So I got 0, 2, and 0, 2. So these are 2-digit numbers. So if there are duplicates, you have to write them both. So now I know that observation 2 and observation 3 are both 2's. And then we have the 8. Well, that's going to be over here as well. Now we're into 1, 2, the number 12. Okay, so that means this is just a 2. The 1 is already here, so we put the 2 there. And then we're going to have a 5, and there's no more numbers that start with a 1. Now let's go to the number 20. And what do you do with 20? Well, the second digit is 0, so you got to write that. And then we got a 21. And that's all there is. There are no 30s, so if there's no numbers, leave it blank. There's nothing goes in there. So we skip ahead to 40, there's just 42, and 45, there are no 50s. So there we have it. Every observation is included here. There should be the same number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 3, there's 5. Yeah, we got everybody. So now, if I wanted to know what the median is, well, I can go up here. The median is between observations 5 and 6. So that's going to be, well, that's 27 divided 13.5. Okay, so between observation 12 and 15. So if we're starting from the bottom, we're going to go first, second, third, fourth, fifth. Well, that fifth observation is 12, and the sixth observation is 15, just like we have there. Oh, hey, we have somebody on chat tonight. Oh, it was somebody spamming us again. So the box and whisker plot can be constructed simply from the observations we have right now. There's your stem and leaf plot. It's quite useful, and it has been making appearances lately on exams, so I'd recommend trying to come to an understanding about this. This gets out of hand. If you have a very large range of numbers, this gets a bit cumbersome, but for small data sets where the numbers are all kind of close together and they have something in common, you can set this up fairly easily. If my range of numbers started from 0. Or not from 0, you could do decimals too, I suppose, but if, let's say, the smallest number was 1 and the largest number was 9,872, this is probably not the way to illustrate that. But for numbers like this works fine. Let's move on. The scatter plot. So the scatter plot, this little rascal here, applies to bivariate data. I'm not going to spend a lot of time on this one tonight because we're going to have an entire discussion over several lectures about this stuff later on in the course. But bivariate data are point pairs. And just like you can see on the sketch, there's an x and a y value. Typically, the x-axis is your explanatory variable. So this is very useful for experiments, I suppose, or where something is manipulated and you want to see the response. That means the response variable is y. So the observations then are these dots. For instance, this one here is at x is equal to 2 and y is equal to 3. That's how we identify that point. Later on, we're going to learn how to compute this line, which is called the simple linear regression line. For now, we're not going to worry about it. I'm just putting it in to show you what's still to come. But basically, we're trying to illustrate the relationship between two measurements. And in this context, works dandy. Keep in mind, both of these must be numerical. You can't have categorical data on the x-axis, not in this course anyway. You can't have categorical data on the response axis. Don't do that. They both have to be numbers, because when we explore this topic in detail, you'll find that we're using the x values and the y values in computations, so they must be numbers that it makes sense to compute mean values, standard deviations, etc., etc. If they're not, you can't do that. Some interesting things that we can learn about this in a more advanced course, but that's not this course, so we're not going to talk about it. So that's, do we have much left here? I think we got one left. No, I think we're done. Okay, there we go. I managed to get all that in an hour. I wasn't sure I was going to make that fit. Well, a little bit more than an hour. Anyway, there we go. Let's go to the new page over here. So, just coming up, what's in the future? Coming up. Now, tomorrow, I believe that we're going to have Lorenzo online to do some teaching. I don't know exactly what he has in mind, but pay attention to Is that how you spell tomorrow? I don't even know how to spell tomorrow. There we go. Okay. Maybe I'll drop a hint on Discord about tomorrow's subject. Adrian and the History of Math will be back. He might be back on Sunday. I don't know what the plan is for Sunday. We're either going to do History of Math or might just do some retro gaming, one or the other. But it means you're going to have Lorenzo tomorrow, and I'm probably going to do some more stats on Saturday, which is 2 days from now. Let's put a big old perhaps there. And we're at the end of the month. We're into May now, so I'm going to take a look at our subscriber list and see who gets math textbooks, just if you're wondering about that. We were doing a little promotion where anybody subscribing to Patreon or our Twitch streams helping us out financially, I'd throw you a math textbook of your choice. I've got a number of them listed. I'm going to get busy sorting that out and get in contact with the winner. All right. So with that in mind, I think I'm going to wrap it up tonight. I think I've talked myself out of gas. So why don't you have a wonderful evening and an even better day tomorrow. Join us for Lorenzo's stream, and probably around, I'm not sure what time he's doing it tomorrow. I was going to say in about 24 hours, but it might be a little bit earlier in the day. We're going to find out. Might be a bit later, too. I don't know. Anyway, I'd like to thank you for joining me tonight, and do take care. And we'll catch you on the next stream. Have a good night, everybody. Bye-bye.